Okay, so this is question number 32 of the Magnetic Fields Homework booklet. So in part A of question 32, what we have is we are told that long cables are used to send electrical power from a supply point to a factory some distance away. So here we have a supply point, some sort of either a substation or alternatively a power station itself. That's connected via long cables to a factory. We're told that there is an input power of 500 kilowatts. So over here, the supply point provides 500 kilowatts at 25,000 volts. So that's supplied to the cables. We're first of all asked to calculate the current in the cables. Now we know the power and we know the voltage or the potential difference. So if we use this equation here and we rearrange it, then the current is the power divided by the potential difference. Power is 500 kilowatts and the potential difference was 25 kilovolts. So if we put that into this equation, we end up with an answer of 20 amps. And you get just 1 mark for getting the correct answer. We're then told that the total resistance in the cables is 30 ohms, and we're asked to calculate the power that's actually supplied to the factory by the cables. So if we go back up to here, and we have a think about our diagram, what's happening is that the supply point is providing 500 kilowatts of power on this side. As the electricity travels down the cables, because the cables have resistance, then some of that energy will be converted into thermal energy as heat, so it will be wasted, and so there'll be less energy or less power at the factory than there was to start with. So, but we can work that out because we know the power from the supply is 500 kilowatts. So the power supplied to the factory will be the power from the supply minus any wasted power from the wires. Now, wasted power is, we virtually always calculate it the same way because wasted power depends upon the current and resistance of the wires by this equation here. So it's an I squared R. So this is sometimes called I squared R heating, or sometimes it's called Joule heating. But basically it's wasting energy in wires because they have a resistance. So we know the current because we've just worked that out, and we know the resistance because it tells us here in the question. So the current was 20 amps, so we've got 20 squared multiplied by 30 gives us 1.2 times 10 to the 4 watts, which is the same as 12 kilowatts. So therefore the power supplied to the factory is our starting power from the supply, which was 500 kilowatts, minus the 12 kilowatts that was wasted as heat, and so it's supplied with 488 kilowatts. There are 2 marks for this question, one for working out the wasted power and then one for actually working out the correct answer in the end. In part 3, we're then asked to calculate the efficiency at which this power is transmitted by the cables. Well, efficiency is basically equal to the power out divided by the power in, and then if you want a percentage, you then multiply it by 100. So the power out was 488 kilowatts. The power in, which was from the supply, was 500 kilowatts. So again, if we have the power out divided by the power in, it gives us 0.976. We want it as a percentage though, because it tells us here in the question that we want this our answer as a percentage, so we need to convert this to a percentage, basically to 2 significant figures, gives us 98%. And then in part B, we're told that in Great Britain, electrical generators at the power stations provide an output of 25 kilovolts. And most homes, offices, etc. are supplied with electricity at 230 volts, and power is transmitted from the power stations via the national grid system. And this diagram here shows us the main principle. So you have your power station, which generates electricity at 25,000 volts. There's then a step-up transformer, which steps up to a very high voltage, and so the current goes down. And then it gradually gets stepped down via a series of step-down transformers down to the voltage that we want in our homes, etc. So we're asked to explain first of all how a step-down transformer differs in construction from a step-up transformer. We simply have to say that a step-down transformer is different because it's got more turns on the primary side than it does on the secondary side. And if you do that, you get 1 mark. If you want to be really kind of accurate, you could then explain that a step-up transformer has got more turns on the secondary side than the primary side, but you can kind of get that from the first bit. So if you just write the first part down, you get 1 mark. In part 2, we're then asked to explain why the secondary windings, so that's the coils of wire on the secondary side of the transformer, So why those wires on a step-down transformer should be made from thicker copper wire than on the primary windings? Well, if you think about it, a step-down transformer makes the voltage go down. So because the voltage on the secondary side goes down, the current goes up. So that's our first point for a step-down transformer. Secondary current is larger than the primary current. In other words, the current in the secondary side of your transformer is bigger than it is on the primary side. And we want to reduce this I squared R heating loss, or this Joule heating loss. And the way we would do that is to make the wires thicker, because if we make the wires thicker, it reduces the resistance of the wires. So again, any two of those points will get you 2 marks. And then for part C, we've then got another written question. We've got a discuss question. So we're asked to discuss the principles that are involved in high voltage transmission systems, and also explain why we use AC and not DC, and also how energy losses are minimised. So there are basically 3 bits, really. We want the principles involved, in particular looking at AC, DC, and then finally look at how energy losses are minimised. So in terms of principles, principles basically means how does it work. So what you've got is voltages are changed using transformers. So that's a principle of the high voltage system. But transformers only work with AC and not DC. And so therefore electricity is generated and transmitted as alternating current. So they're kind of like the principles in high voltage transmission systems. We then need to explain or say why energy losses happen and also why they're minimised. So in terms of energy losses, the main source of energy loss is this I squared R heating again, so this Joule heating. So to minimise these losses, what we really want is we want the resistance of all the cables to be as low as possible. I squared R losses are reduced if the resistance is small, but also if the current is small. If we increase the potential difference, that lowers the current. So if you've got high potential difference, you've got a smaller proportion of power is wasted. But potential difference has to be reduced as it reaches the consumers in people's houses and factories, for example, for safety, and that's done in stages. But transformers themselves can cause energy losses, but these are reduced, for example, by laminating the core, having thicker wires, putting the primary and the secondary coils close together. So really, what you really want is you have to say something about the principles, you have to say something about the energy losses, but if you say basically those 3 things and you have a linked up argument here about how you reduce, about what the energy losses are and how you reduce them, then potentially you get 6 marks for that. So that was question number 32 of the Magnetic Fields homework booklet.